All right, let's dive in. Today, we're going to uncover a hidden pattern that really shapes how we understand health. Whether you're in a public health office in Accra or a maternity ward in the Ashanti region, it's this powerful shape that helps us turn what looks like chaos into something clear.
So you have to wonder, right? How do health professionals make any sense of it all? I mean, they're just flooded with data. Hundreds of lab results, thousands of birth weights. How do you find the signal in all that noise? Well, that's the exact question that biostatistics helps us answer every single day.
To make this feel real, let's just imagine this with me. Picture a midwife in a busy Ghanaian hospital. She's just wrapped up a long shift, and she's got the records for the last 100 babies born. And at first glance, the numbers for their birth weights, they just seem totally random.
You know, one baby is 2.8 kilograms, a good healthy weight.
The next one is a little bit heavier, comes in at 3.2 kilograms, also perfectly fine.
And another is a bit lighter, 2.6. See? Each number is just its own little piece of data.
But this is where the magic really starts to happen. When we stop looking at each individual number and we zoom out to see the whole picture. When she plots all 100 of those weights on a graph, something amazing takes place. A clear, distinct, and actually a very familiar shape starts to form right out of all that randomness.
So what is this shape? Well, this elegant curve has a name, and it happens to be one of the most important ideas in all of statistics and health sciences. We call it the bell curve.
Now, the official name for this pattern is the normal distribution, and you find it pretty much everywhere in biology. Things like height, blood pressure, and yep, you guessed it, birth weights. What it shows us is that most measurements tend to bunch up right there in the middle, around the average, and the really high or really low measurements, they get a lot rarer.
What's so cool about the bell curve is how its main features basically define what we think of as normal. For starters, it's perfectly symmetrical, a mirror image on both sides. And get this, the mean, which is the average, the median, the middle number, and the mode, the most common number, they are all the exact same value, sitting right at the very top of that curve.
Okay, so this bell curve isn't just a pretty shape. It's got this predictable, really reliable structure. And that is what takes medicine from just observing things to being a real data-driven science. It's almost like a secret code for reading data, and once you know the rule, you can unlock insights in an instant. So here's the first part of that code. In any normally distributed data, about 68%, so a little more than 2/3 of everything you measure, is going to be super close to the average. Specifically, it's within what we call one standard deviation. Just think of a standard deviation as a standard-sized step away from the center.
Now, if you take two of those standard steps out from the average on either side, you've suddenly captured about 95% of everybody. And this range is absolutely crucial. In healthcare, this 95% zone is very often what we consider the normal range for all kinds of clinical tests, from blood sugar to cholesterol. And finally, if you go 3 standard steps out from the middle, you've basically accounted for everyone, 99.7% of all the data points. This tells us something really important. Values that fall outside of this range are incredibly rare. They're true outliers, and they could signal that there's a potential health issue to look into.
Okay, so let's jump back to our midwife. If she does the math and finds the average weight is 3.0 kilograms, and that standard step, the standard deviation, is 0.5 kilogram, she immediately knows the expected weight range for almost every single baby. 95% of newborns are going to weigh somewhere between 2.0 and 4.0 kilograms. It's an incredibly powerful shortcut in a clinical setting.
So knowing the pattern for a whole group of people is great, but, healthcare happens one patient at a time. So how does this big bell curve actually help a doctor or a nurse with the measurement from just a single patient?
The answer is something called the Z-score. And let me tell you, the Z-score is this amazing tool that lets us put any measurement onto one universal scale. It tells you exactly how many of those standard steps a patient's value is away from the average. It's what lets us compare apples and oranges, or in our case, something like blood pressure with cholesterol levels. And you know what the best part is? It's a beautifully simple 3-step calculation. You just take the patient's number, you subtract the population average, and then you divide the result by that standard step size. And just like that, a raw number becomes a truly meaningful insight.
And this is why the Z-score is such a game changer. It gives you context. A blood pressure reading of 140. What does that even mean on its own? Is it high? I don't know.
But a z-score of positive 2.0 tells a health worker immediately that, yes, this value is unusually high. It's actually higher than about 97.5% of the population. The z-score doesn't just tell you what a number is, it tells you what it means.
So, at the end of the day, why should this elegant little bell curve matter to you? Whether you're a student, a patient, or a professional in the field, why is this one shape so fundamental to everything?
Well, it's because from the local clinic all the way up to national health policy, the normal distribution is a basic, essential tool for making smart, evidence-based decisions right here in Ghana. It's used to set the normal ranges for every single lab test you take. Public health programs use these scores to track child growth and catch malnutrition early. And it helps researchers understand the health of entire communities at once.
The normal distribution is such a powerful, predictable pattern in health. But what's really fascinating is that its beautiful shape shows up everywhere, in finance, in nature, in social sciences, which kind of leaves us with a final thought to chew on. What other complex problems could we solve if we just knew to look for that simple, elegant bell curve hiding in the data all around us?